Hey there, everybody. Welcome back. It's Sean Lally, your physics pal here. And I want to talk to you today about how we figured out, about 2,500 years ago, as it turns out, the size of the Earth. So if you remember a couple of videos ago, I was talking about SI standards. And one of the standards, the meter, was specifically linked to the size of the Earth. In fact, it was defined as 1/10,000,000th the distance from the North Pole to the equator. So that was done about 225 years ago, but believe it or not, over two millennia ago, we actually were able to calculate and measure the size of the Earth. So let's talk today about how that was done. So in order to understand this, we have to go back and think a little bit about some geometry. So you may have had high school geometry before. You probably did. And you may have thought, well, geez, this doesn't seem like it's good for much. As it turns out, it was the form of mathematics to the ancient Greeks, and really up until the scientific revolution and beyond. So measuring the size of the Earth, of course, has something to do with mathematics. Let's go back to the days of the ancient Greeks, our friends, and a specific Greek known as Eratosthenes of Cyrene. Now, he lived approximately 276 to 194 BCE, or BC if you prefer. Now, it was known by locals that Syene, or Aswan, in Egypt, it might actually be Aswan. I had an Egyptian student last semester who corrected me, and she's not here to correct me now, so I think it is Aswan. In Egypt, was located at or near the Tropic of Cancer, which is, in fact, a circle of latitude around the Earth close to 23.5 degrees north. Now, this location is important because the sun is directly overhead at noon on the day of the summer solstice, and no object casts a shadow at that time and point. Also, you could see to the bottom of a very deep well. Now, of course, what this has to do with is the fact that the Earth is inclined at an angle of 23.5 degrees, and yes, this has a lot to do with why there will be no shadow here on the summer solstice. But anyway, with that in mind, Eratosthenes devised a wonderful and clever experiment. For he knew of another location, Alexandria, that was north of Syene by about 5,000 stades, which can be converted to kilometers, which it works out to be about 800 kilometers. Now, at noon on the same day of the summer solstice, Eratosthenes set up a large pole, which did cast a shadow at noon when in Alexandria, when the shadow effect was actually shortest there. He was able to determine the size of the shadow and the angle from the top of the stick to the far side of the base. So with this, we actually end up with a pretty clever experiment. Now, this is really hard to put into words, so I do have a couple of pictures to show you next. But anyway, think of this. The distance from Syene to Alexandria was known, and the shadow and angle were pretty easy to measure accurately, or at least reasonably accurately. How could you go about using this information to determine the size of the Earth? Well, it ends up being a geometry problem. You might think of it as a geometry problem, perhaps even elementary trigonometry, but really it's just Euclidean geometry. So here it is. This picture, my friends, is not to scale. Okay, so here we have a picture of the Earth. Look at the well at Syene, or Aswan. So imagine at this time you can see to the bottom of that. Now imagine that this is a straight well that is drilled deep into the Earth. It might go down a few hundred feet, for example. Now, if you could imagine a straight line going into that well, it would in fact go directly to the center of the Earth if it is a straight well into the Earth. So you've got basically the first dotted line goes from the well to the center of the Earth. On the other hand, let's go take a look at this pole that was 800 kilometers or so north. Now, that pole being 800 kilometers north of the Tropic of Cancer, in fact, is going to cast a shadow. Now, that shadow worked out to be about 7.2 degrees or so. So, now if you can imagine the sun is pretty far away, it's about 8.5 light minutes or so, about about 93 million miles, 150 million kilometers, so that the rays coming from the sun are approximately parallel. On the other hand, the reason why, in fact, the pole casts a shadow to begin with is because these roughly parallel rays coming from the sun, well, the one right here into the well is essentially directly overhead, but this guy is not so much overhead relative to the Earth. So this casts a shadow. Now this pole, if this is erected directly straight into the Earth, it too could form a dotted line that goes into the center of the Earth, and that would meet the dotted line that comes from the well at Syene or Aswan. So, take a look at the little map over here from Syene to Alexandria. 5,000 stadia apart, or stades apart. That's 800 kilometers. And we end up with a problem that can be solved by proportion. All right. Again, it's not terribly obvious. It really is not. That's why we remember Eratosthenes, because he was pretty clever. Two rays of sunlight drawn on the picture. They're very nearly parallel to each other. In fact, we can say that they are, for all intents and purposes, parallel. Now, the two sticks, or a stick in a deep well, are long enough, again, they would intersect at the center of the Earth. And that creates an angle between them. But here's the geometry part. The angle is the same between the top stick and the ray of sunlight as the angle in the Earth. Let's go back. So, this angle in between the top of the sunlight and the pole is actually the same, it's about 7 degrees for this experiment, as the angle in here inside the Earth between these two dotted lines. You're thinking, oh my gosh, how would we know that? Well, if you took geometry, you might remember that two parallel lines, when cut by a transversal, give alternate interior angles that are equal. Now, most people don't remember that sort of thing, I would imagine, but alternate interior angles, or maybe z angles, depending on how you learn your geometry, those are equal according to Euclidean geometry. And actually, they kind of look equal in this picture anyway, even though you really shouldn't just trust that, especially in this not to scale picture. Okay, so, again, if you don't know the geometry or remember it, you might have to suspend a little bit of disbelief. But once you see it, the problem is a simple proportion. How many degrees are in a complete trip around a circle? Well, you probably know this. It's 360 degrees around a circle. We can thank our friends, the ancient Babylonians, for that, who were interested in inscribing a hexagon in a circle problem. You combine that with a base 60 numerical system, and, well, there you are. You get 360 degrees. That's a story for another day. So, here's the math. The angle was about 7 degrees. I think it's actually closer to 7.2. So here's the proportion. The angle of 7 degrees is to the complete distance around a circle, which is in degrees, it'd be 360 degrees, as the distance between Syene and Alexandria is to the complete distance around the Earth, or otherwise known as the circumference. A little hard to put into words, so let's make it up in terms of an equation. 7 is to 360, as 800 kilometers is to the circumference of the Earth. Now, that's pretty easy. You could do a little bit of cross multiplication there, or a little bit of basic math proportions, and that gives you a circumference of the Earth of about 41,000 kilometers. 41,000 kilometers, that does work out to be about 25,000 miles for the circumference of the Earth. Okay, now you're probably thinking, well, I guess I'll trust you here, Sean, but how close is that to the currently accepted value that we can get from modern astronomy? Well, check this out. The current value for the approximate circumference of the Earth is about 40,030 kilometers, which again is about 25,000 miles. Eratosthenes was within 3% of the currently accepted value. Not bad for sticks and string. Not bad for shadows and protractors, huh? I don't know about you, but if you remember doing any high school experiments and you got a 3% error, you were probably pretty proud of that. So, yeah. So let's hear it for Eratosthenes. He's our hero of the day. And I hope you enjoyed this. Otherwise, see you soon. See you on the moon. Bye-bye.